Okay, so in the last lecture we studied a very important result of a compact metric space in general, and it was Hein-Borel theorem, which said that whenever you have in R set is compact if and only if it is closed and bounded. So that was very famous Hein-Borel theorem. At the end we have said that same thing we can generalize in case of Rn also. I have given you as an exercise that subset of Rn is closed and bounded if it is compact. Now in case of Rn, the closed interval AB has a different format. Naturally it will be a subset of R. If I take k dimensional metric space, n dimensional or k dimensional, anything, then we are interested in defining what is meant by k cell, and we will prove that k cell is compact as it was done in case of R. Closed interval AB is compact. Similarly, we will prove that k cell is compact. So you must first understand what is k cell. If you understand what is k cell, then the arguments that we are making in proving that k cell is compact are also beautiful. So the main aim here is to define what is k cell, and the result that we are going to prove is this theorem: k cell is compact. K cell is compact. Okay. So what is k cell? Suppose I take I as a k cell. I is the name of that k cell. Then it is a subset of Rk. So it will consist of k tuples x1 up to xk, where x1 will be in between a1 and b1, right? x1 will be such that a1 is less than or equal to x1 less than or equal to b1. x2 will be between a2 and b2, so a2 less than or equal to x2 less than or equal to b2, and so on. ak less than or equal to xk less than or equal to bk. Set of all such k tuples will form a k cell. Okay. So let I be a k cell. Proof of this now. Let I be a k cell. Now what do you mean by this? It consists of the point, it consists of points of the type x, where it is x1, x2 and so on up to xk, such that ai, or we can say aj, is less than or equal to xj less than or equal to bj, and j takes values from 1 to k. So 1 less than or equal to j less than or equal to k. So this is the definition of k cell. As it is points of the type x1 up to xk, you immediately come to know that this is subset of Rk. Now if you consider a special case of this, suppose I consider 2 cell. This is to understand the idea. 2 cell. 2 cell will be the points of the type x, x1, x2. And so here it will be what? A1 less than or equal to x1 less than or equal to b1, and also a2 less than or equal to x2 less than or equal to b2. So this is a subset of R2. Suppose this is your xy axis, and you take a1 here, b1 here on x axis, and a2 here on and b2 here on y axis. Then this rectangle that we will have is 2 cell. This is rectangle. Actually this rectangle is a what we can say avatar of interval in R. If you consider R3, it will be rectangular parallelepiped. So it will be any element in that rectangular parallelepiped, which is an element of R3, can be written as x1, x2, x3, where x1 will lie between a1 and b1, x2 will lie between a2 and b2, and x3 along z axis from a3 to b3. So z coordinate lies between a3, b3, x coordinate lying between a1, b1, and y coordinate lying between a2, b2. Such a rectangular parallelepiped will be 3 cell in R3. So this is k cell that we are talking about, right? You have to imagine. See, mathematics can be best understood by visualization. You should be able to visualize what will happen in R3, what will happen in R2. Without help of computers on blackboard, we cannot draw all these 3-dimensional or more multi-dimensional figures you cannot draw, but whenever you consider their special cases in R, what is the special case in R2, what is its special case in R3, then idea come to your mind. So this is a 2 cell, remember, this is a 2 cell. Okay. Now what we can also see here is this, that if you now take this point, suppose now this point when you take, it is A1 A2, okay, and this point we can take is as B1 B2. Now this diagonal when you take, what is the length of this diagonal? It will be B2 minus A2, okay, square, and plus B1 minus A1 square and root of this. This is the diagonal, or we can say this is the diameter of this 2 cell. So any 2 points of this when you take, the distance between any 2 points will be less than this diagonal. So what I can say is, if I take x and y belonging to this 2 cell, suppose I call this as I, then distance between x and y, here it will be norm. Now in R2 if I take Euclidean distance, it is norm of x minus y. This will be less than, if I take this as delta, you can say this is less than or equal to delta. Any 2 points in that, whenever I take, distance will be less than or equal to delta, right? So that is the diameter, and this is the idea behind diameter. Diameter is the largest distance of between any 2 points of that set. So this is what it means. Okay. So mod of x minus y or norm of x minus y, in general I will say mod of x minus y, because that will be less than or equal to delta. Notation somewhat I am changing in this lecture. Mod of x minus y is less than delta, because where delta is this. So in general what I can say, in general, instead of B2 minus A2, B1 minus A1, this is only 2 pairs we have, because this is the diagram that we have drawn in R2. But whenever you go to RK, what will be this? It will be Bj minus Aj square summation. In case of K cell, this thing will be summation of what? Bj minus Aj bracket squared, j taking values from 1 to k, and then root of this, because whole square root I have to take. This will be delta. And so any 2 points in RK when I take, or K cell when I take, x and y, distance between them, mod of x minus y, distance will be denoted by mod of x minus y in general now. So that mod of x minus y will be less than or equal to this delta. This is what we are going to use in the proof of this theorem. And this is a special example I have given, R2. This is not the final thing. This is just a special case. Okay. And also we are going to use in this particular result one theorem called as a nested interval theorem. What is that theorem telling? If In is a sequence, okay, if In is a sequence of intervals in R1, In is sequence of intervals in R1 such that In contains In plus 1, In contains In plus 1, where n takes values from 1, 2, 3 and so on. Then it says that intersection of In is not empty. This is not empty. N takes values from 1 to infinity. This intersection is not empty. This is nested interval theorem. And same thing we can do for in Rk. So if k is a positive integer and In is a sequence of k cells, this is sequence of intervals in R1. But interval in R1 will take form of k cell in Rk. Are you getting? Interval in R1 is k cell. Whenever you consider in Rk, it's a k cell. And so if I take nested k cells, right? Suppose in R2 I take nested 2 cells. That means what? This is one I1. Inside this is I2. Inside this is I3. Inside this is I4. When you go on like this, its intersection is not empty. This is what this theorem tells. Nested interval theorem. So this also we are going to use. Okay. So now we will start with the proof actually. What we have to prove is this, that K cell is a compact set. Now what we will do in this? First we have defined what is K cell. This is the K cell. So it is a subset of Rk. Okay. Its special case in R2 will be interval, in rectangle, in R it will be interval, like that. And we will put delta is equal to, as I said, it is summation j taking values from 1 to k, bj minus aj squared and raised to 1/2. This is delta. Then mod of x minus y is less than or equal to delta for all x and y belonging to K cell, which is I. Right? I be a K cell, we have said. So it is I. Now what I want to prove? To prove that I is compact. To prove that I is compact. I want to prove I is compact. So by that what I want to prove? That if you have any open cover, then it contains a finite subcover of I. Okay. So that is to prove that every open cover of I, has a finite subcover. Every open cover of I has a finite subcover. This is what we have to prove. Okay. So we will assume contrary. Assume contrary. What do you mean by that? That is, we assume I is not compact. Not compact. This is what we are assuming. When it is compact, what you know? Every open cover has a finite subcover. Whenever I am saying it is not so, then what? You can find an open cover, right? You can find an open cover such that there is no finite subcover to this I. So we assume that I is not compact. That is, there exists open cover, say G lambda, there exists open cover G lambda such that it has no finite subcover. G lambda of I, there exists open cover G lambda of I such that it has no finite subcover. No finite subcover. This is what we are assuming. Now what you do is, in case of R2 we will try to understand the procedure. Suppose this is your 2 cell, this is your A1, this is B1, this is your A2 and this is B2. Okay, now what you do is take midpoint of this, say this is say A1 B1, so it is say C1, and A2 B2, say midpoint is C2. So you take Cj as in short, Cj we will take as A1 B1 upon 2 is C1, A2 B2 upon 2 is C2, and then what you do is join these midpoints. So what you have done is broken this 2 cell into 4 parts. Same thing we will do in case of Rk. What I will do is, I will set Cj as Aj plus Bj upon 2. How many such points I will get? K points. And then I will break the, now in how many parts this has been broken? In 4 parts. That means 2 square, because this was 2 cell actually. Whenever I take K cell, and if I take midpoints of all Ai and Bi, Aj and Bj, and take Cj as Aj plus Bj upon 2, then joining all these things, joining what is being joined? See, we just join this. Similarly in Rk, we have to visualize that. What will be the K cell? It will be broken into how many parts? K cell will be broken into 2 raised to K parts. This is 2 square parts because 4. It has been broken in 4 parts because this is 2 cell. In K cell it will be 2 raised to K. Subcells will be there. All of them will be K cells. See here all the parts are 2 cells. So whenever I divide it in, whenever I am considering Rk, and if I choose these midpoints and join them, the K cell is broken into 2 raised to K cells. Okay. So here what I will say is no finite subcover. Okay. Now what you do is put Cj as Aj plus Bj upon 2. Okay. The intervals Aj Cj and Cj Bj determine 2 raised to K cells. 2 raised to K cells whose union is I. 2 raised to K cells, we will call them as Qi. Okay. Each of them is a K cell such that union of Qi is nothing but I, the basic K cell. See, union of these 2 cells is again the basic 2 cell I. Have you understood? So this is what we have done. Okay. Now the main statement is at least one of these Qi K cells, right? We will say now what we are saying here is this. See, it has no finite subcover. This is what we are saying. This I has no finite subcover. Now what we have done is taken this Cj and then Aj Cj and Cj Bj, they will form how many K cells? 2 raised to K cells. Each of them we will call as Qi and their union is I. Now you are saying the whole set I K cell is not covered by finitely many. It has no finite subcover. So at least one of these Qi, how many Qi's are there? 2 raised to K. It will not be covered by finitely many subsets of G lambda. Why? Because if everything is covered by finitely many subsets, then their union is also, because suppose this is covered by say 10 subsets of G lambda, that open cover. This is suppose covered by 15, this is suppose covered by 20, this is suppose covered by 30, then 30, 20, 15, 10, all that is finite number, addition is finite number. So that means what? I will be covered, but we are saying there is no finite subcover. See, we are saying there is no finite subcover. What does it mean? There will be at least one of these Qi's. Here I will say suppose this is that, this is suppose that Q1. This is not covered by finitely many subsets. Understood? If we do not assume this, then everything is covered by finitely many subsets, which is contradiction to your assumption. Okay. So what we will say now is this, that at least one of these, at least one of these 2 raised to K cells, 2 raised to K cells will not be covered by finitely many, will not be covered by finitely many subsets of G lambda. Okay, why? Otherwise, we can say in bracket, otherwise I will be covered. Otherwise, I will be covered by finitely many subsets of this G lambda. We next subdivide this I1. Okay. Now at least one of these, 2 raised to K cells, say I1, we will call it as I1, will not be covered by finitely many subsets. Now what you do is again subdivide this I1. Subdivide I1 by using this procedure. For example, here when I take I1, This is divided again by taking their midpoints into 4 parts. Again same logic we will use. At least one of these 4 parts is not covered by finitely many subsets of G lambda, because if it is so, then everything is covered by finitely many, and that is not the case. So subdivide I1, okay, and continue the process. What will happen when I continue the process? We obtain a sequence In. We obtain sequence In. We obtain the sequence In with the following properties. We obtain sequence In with following properties. What are those properties? First thing is, you know that I1, or basic thing it contains I1, it contains I2, it contains I3. So these are nested K cells that we are getting. Remember, these are nested K cells. Then each of them, so B, each of them, In is not covered. In is not covered by finitely many subsets of G lambda. Finitely many subsets of G lambda. And you know that if C part, if X and Y belong to In, then mod of X minus Y is less than or equal to 2 raised to minus n into delta. These are the properties that this In will possess. This is also obvious because any 2 elements of I when you take, they are less than or equal to delta. Whenever I take any 2 elements of I1, they will be less than or equal to delta upon 2, then delta upon 4, like that. So delta upon 2 raised to n will be the diameter of any In that we will have. It depends on what is n. Okay. Now I have already told you about the theorem of nested K cells. So these are nested K cells because I contains I1, I1 contains I2, I2 contains I3. So these are all nested K cells. So by that theorem, their intersection is non-empty. So there exists at least one point, say X star, which belongs to all In. Remember. So by that theorem, so by nested K cells theorem, there exists a point X star, which is in every In, there is a point X star which is in every In. For some alpha, okay, but then this In will be, see, you have first we have assumed that G lambda belonging to capital lambda, G lambda, that this thing, open sets G lambda, that covers I. Now X star is in all these In, so X star is an element of I. So it is also covered by that G lambda, so one set G lambda, one set from G lambda. Okay. So there exists a G alpha such that X star belongs to G alpha. But what is G alpha? It is an open set, and you know the properties of open set from metric topology, that whenever any element belongs to an open set, it is interior point of that set. And so there exists some, say we can say R greater than 0, such that SXR or open sphere around X star with radius R will be entirely inside G alpha. So there this implies what? X star is interior point of G alpha. X star is interior point of G alpha. So there exists R greater than 0 such that SXR is subset of. Okay. So now we have X star. X star is the point which is in all these INs, right? Now that means what? X star is element of I is covered by that G lambda. So there exists some open set, say G alpha, to which X star belongs. Now as X star is element of open set, it is interior point of G alpha. So you can find some R greater than 0 such that Sxr is subset of G alpha. Now if you take Y belonging to Sxr, if you take Y belonging to Sxr, then Y also is in G alpha. Okay. So if I take Y belonging to Sxr, what I know? Distance between Y and X, or we can say mod of Y minus X star, Sx star R. This is Sx star R, right? So Y minus X star, this will be less than R, and this implies Y also belongs to G alpha. Y also belongs to G alpha. If n is so large, now I can make n. So if n is so large that 2 raised to minus n into delta, 2 raised to minus n into delta is less than R. Okay, this is obviously possible because I can make n as large as possible and take care that delta upon 2 raised to n will be less than R. Okay, so there is such n, there should be such definitely n, so there exists such n. Otherwise what will happen? 2 raised to n will be less than delta upon R. 2 raised to n will be less than delta upon R for all positive integers n, for all n belonging to capital N, which is contradiction. This is contradiction to Archimedean property. This is contradiction to Archimedean property. Okay. So such n definitely exists. So what does that implies now? If x and y belongs to n, mod of x minus y, this is the third property that we have of this observation. And so this means here also we have said that 2 raised to n is less than means 2 raised to, this R is greater than delta upon 2 raised to n, and this is delta upon 2 raised to n. What does this mean? This means your In, whole In is subset of G alpha. Obvious, because see, what we are saying is if x and y belong to n, mod of x minus y is less than delta upon 2 raised to n. And here we are saying x star and y both are in G alpha, and distance between x star and y is less than R. So I can make n so large that delta upon 2 raised to n will be less than R, and that means both x and y, they will belong to that G alpha. Okay, that means any 2 points of x and y, the diameter of that In is diameter of In by observation is delta upon 2 raised to n. And here we are saying x and y, you take any 2 points or x star and y, any 2 points of that, when you take, the distance between them is less than R, and we are making R greater than delta upon 2 raised to n. All these things implies In is subset of G alpha. Okay, which is contradiction. This is contradiction. Why contradiction? Because only one set G alpha is covering In, and here we are saying In is not covered by finitely many subsets of G lambda. So this is the contradiction, and that proves that this thing is not so. Okay, and this completes the proof. So this is contradiction, hence your assumption was wrong. And what is the correct thing then? K cell is compact. K cell is compact. So this is obviously one important result. And see here we are using nested interval theorem, nested interval, or you can say nested K cell theorem we are using. Whenever you have a collection of K cells which is nested, that means inside one K cell another K cell, inside that another K cell, then their intersection is non-empty. This is what it says. And now naturally these are all bounded sets. K cell is bounded, right, as interval in R is bounded, rectangle in R2 is bounded, rectangular parallelepiped is bounded, because the diameter of them is finite. See, the concept of bounded sets in metric spaces we are using here profoundly, and this is about K cell is compact. So that is now many results about compact sets we have proved in all these lectures. Also we have dealt with connectedness, compactness, then complete metric spaces, then we have also seen sequences in metric spaces. All such actually constitutes the metric topology. Now one or two problems I will discuss from metric spaces, and that also about compact metric spaces. See, the first problem is that we will discuss is not about C, it is something like this, that suppose you have subsets of R2 are given and you want to prove they are compact. What to do? See, suppose I take see, R2D is our metric space that we are considering, usual distance, and suppose I take this set, first set that I take is x comma y, okay, belonging to R2, x comma y belonging to R2, such that mod of x is less than or equal to 1. Mod of x is less than or equal to 1. So which is the set? Can you visualize this? Mod x less than or equal to 1. There is no restriction on y. So if you draw this x and y axis, then you know mod x is less than or equal to 1. So suppose it is 1 here. Mod x is less than or equal to 1. So it will be from this, no, minus 1 to plus 1. Mod x is less than or equal to 1. Any of these minus 1 to plus 1 when I take, and any number between them, then mod x is less than 1. And there is no restriction on y. So y can be anywhere from this. So whole this set, if I draw a line parallel to y axis here, this is the line x is equal to minus 1, and this is the line x is equal to plus 1. This is y axis and this is your x axis. So this thing is this set, mod x is less than or equal to 1. Is it bounded? See, we have proved the result. What is that result? If it is closed and bounded, it is compact. In Rn, if a set is closed and bounded, it is compact, and conversely. Now we have to discuss this thing, whether this is closed and bounded, first thing, right? See, infinite set, this is not bounded first. This set is not bounded. Clearly it indicates. But also you can prove it something like this. If you take a point, say 1 upon 2 comma m, right? Consider a point 1 upon 2 comma m belonging to R2. M is any real number. So for any say m belonging to R plus, for any m belonging to R plus, that means positive real numbers, you can easily see that 1 upon 2 comma m, this point 1 upon 2 comma m belongs to this set. Suppose I call this set as E, then it belongs to this set E, right? Because 1 upon 2, you know, this satisfies this property, mod x less than or equal to 1. There is no restriction on y coordinate. So any point in this phi we are taking. Now if you calculate the norm of this point, norm of 1 upon 2 comma m, what is this norm? It is equal to, you know, norm of x comma y is root of x square plus y square. So it is 1 by 4 plus m square, okay, and this is definitely greater than or equal to m square, and so this is greater than m, and so m is any real number and this norm is greater than that. So definitely set is not bounded, and as it is not bounded, this cannot be compact. So this set is not compact. So this set E is not bounded because it is greater than m. Remember, it is greater than m, so not bounded, and so E is not compact. E is not compact. Another example we will try. Suppose I am given the set x comma y. Second example, E is the set, suppose, of R2, again x comma y, such that x greater than or equal to 1 and 0 is less than or equal to y less than or equal to 1 by x. This set is given. whether this set is compact, like this. So you have to use the result that set in Rn is compact if and only if it is closed and bounded. That is the result. So if I prove that this is closed and bounded, this is compact, otherwise not. Okay. So very simple techniques. First thing is you should be able to visualize what is the set. Right. Generally at TY BSc level they will ask you the problems in R2. So in R2 you should know that in general in Rn also, whenever set is closed and bounded, it is compact. So whatever set is given, whether it is closed and bounded, rectangle is bounded, interval is bounded, rectangular parallelepiped is, but then this particular set, what is the nature of this set? What are the elements in this set? That is important. So here suppose I take this set as E, then for any m greater than or equal to 1, for all m greater than or equal to 1, because we want x greater than or equal to 1. If you take what? Okay, if you take m comma 1 upon m, will it satisfy this thing? M comma 1 upon m, it will belong to this set. M comma 1 upon n will belong to the set E. Why? Because we are saying m is greater than or equal to 1. So this condition is true. And what is y? Y we have taken 1 upon m. That means y is taken as x, when x is m, y is 1 upon m. So y is equal to 1 upon x. That condition is also satisfied. Okay. Now so this is the point in that. If you consider its norm of m comma 1 upon m, then what is that? It is equal to root of m square plus 1 upon m square. Again same story, as m is greater than or equal to 1, 1 upon m square is positive. So this is greater than m square. Okay, greater than root of m square, and so it is m. And now so m can be any real number. So norm is not bounded. So norm is not finite because it all depends on m. So what does this mean? It is not bounded set. E is not bounded. E is not bounded, and so E is not compact. E is not compact. So just we have to consider this thing, whether it is bounded or not bounded. That we can check. And if it is closed and bounded, then it is compact. Then last problem we will study. Suppose I am given this set. S is suppose the set x comma y, where x square means x comma y definitely belonging to R2, and the set is x square minus y square is equal to 1. This set is S compact. Is S compact? This is asked. So what we can do here, you take 2 points. If I prove that this is closed and bounded, then it is compact. So what you do is you take m belonging to R plus some positive real number R plus, and if I take the point say root of 1 plus m square comma m, then this belongs to S, because see here, this is your x, here x we have taken as root of 1 plus m square and y we have taken as m, and you can see here x squared minus y squared is 1. So this condition is satisfied. So this is the point in S. But what now, where m is any positive real number, now what will be norm of this? Norm of this point. Which point? Root of 1 plus m square comma m. So it will be what? It will be root of 1 plus m square, because square of this, and minus m square. So it is what? It is 1. Norm of x square plus y square, sorry. So this is 1 plus m square, and so it will be root of 1 plus 2m squared, and this 1 plus 2m square is definitely greater than root of 2m squared, which is greater than root of m square, and so it is m. Again we can see that it all depends on m. So if m is large, then norm is also going to be increased. And so here also we can say that this set is not bounded, and as it is not bounded, it is not compact. Okay. So this is one simple technique by which you can prove whether the set is bounded or means set is bounded. Whenever I want to prove what I want to show is norm of every element in that is finite, but here norm depends on m. So if as m goes on increasing, norm will be unbounded, and so these sets are not bounded, and when the set is not bounded, it is not compact, because that theorem we are using. Closed and bounded subsets in Rn, they are compact, and conversely also. But as it is not bounded, all these three examples that we have done, sets were not bounded, and so they cannot be compact. Okay, so this is what I wanted to put in all these lectures. We have started with simple ideas in metric spaces and reached up to compactness. All the rigorous results also we have discussed. If in future we can talk about path connectedness, also we can talk about some ideas in uniform continuity, continuous functions, and also some graded results in Rn, because this is generalized metric spaces that we have taken, but Rn is a special case of metric space, R is a special case of metric space. So analysis contains lots of results, and whenever you change the domain, the behavior of the function also changes, always we know, and so there are lot of fantastic results that we can discuss in future. Thank you.